Hi, I'm Langston Wilcox, and today I'll be presenting Lab 6 Magnetic Molasses. The purpose of this lab was to analyze how a magnet falls through an aluminum tube, comparing real-world data to simulations. We assumed negligible air resistance, focusing on only gravity and magnetic forces. Interestingly, our observed fall time was 0.18 seconds, while our simulated predicted 0.28 seconds. A discrepancy we'll investigate further. This experiment hinges on key physics principles, like magnetic flux, which describes the magnet's interaction with the tube, Biot-Savart's law, which governs the magnetic field from induced currents, Faraday's law, which explains how the tube's motion generates currents, Lorentz force, which results the opposition of the magnet's fall, and Ohm's law, which links current and resistance. Together, these create the magnetic molasses effect. We conducted the experiment by dropping a magnet through an aluminum tube 5 times, recording each fall with a video stopwatch. First, we used a magnetometer app to identify the magnet's north pole, ensuring consistent orientation. The tube's length, 0.46 meters, and radius, 0.23 meters, were fixed, and the magnet's mass, 0.02 kilograms, was measured. This method aimed to minimize variables for reliable data. Our trials yielded an average fall time of 0.18 seconds, with most times clustering around 0.2 seconds. Trial 2's 0.1 second was an outlier likely due to timing error. The tube's dimensions and the magnet's mass were carefully noted, but the gap between the observed and simulated times 0.18 second and 0.28 seconds suggests an unaccounted force like friction or air resistance. The code here simulates the magnet's velocity, predicting a fall time of 0.28 seconds, longer than observed. The overestimation hints at model simplifications, such as ignoring air resistance or assuming ideal conditions. Refining these parameters could bridge the gap between theory and experiment. Here is the last half of my code. A theoretical velocity time graph would show the magnet decelerating as it falls, due to opposing magnetic forces. The simulation's time into 0.282 seconds further highlights the overestimation compared to real data, 0.18 seconds, reinforcing the need to account for real-world complexities in models. Several factors may explain the discrepancies. Video stopwatch delays, misaligned magnet polarity, unaccounted air resistance, and friction between the magnet and tube are a few examples. While our models simplified these, their real-world presence likely shortened the fall time, underscoring the challenges of perfect simulation. Here are my answers to the two what-if discussion questions. First, lower resistance in the tube increases induced current, strengthening the opposing field and slowing the magnet further. Next, fewer loops in the tube weaken the field, letting the magnet fall faster. Both of these answers align with Faraday's and Lenz's laws, demonstrating how material properties and geometry shape magnetic damping. In conclusion, magnetic damping visibly showed the magnet's fall, but real-world results diverge from simulations due to unmodeled forces. This lab highlights the importance of balancing theoretical assumptions with practical constraints. Thank you.